Changes of states of matter. So let's begin with this. Do we actually know what matter is in reality? So, what is matter composed of? Matter is something that has mass and takes up space. It's made of small, minute particles or entities known as atoms, and it mainly is described in four main states such as solids, liquids, gases, and plasma. Now let's distinguish between the three states and have a quick recap. First comes solids. Here the particles are tightly packed to each other. They have a definite shape and volume and have very strong intermolecular or interparticular forces. They are not compressible at all, very rigid, and the particles do not move but they vibrate in their fixed positions. Liquids. Particles are packed closely but together but to an extent. They do not have a definite shape and they fill up the shape of the container. They have weak intermolecular or interparticular forces and they can be compressed to an extent or to a limit. They are not rigid at all and the particles are free to move. They move or slide past one another. Lastly, gases. Here they are very loosely packed, they do not have a definite shape or volume, and they expand to fill up the container. They have very weak intermolecular or interparticular force of attraction, and they are easily compressed. They are not rigid at all, and the particles move very freely. To describe this, there is a diagram given here where it explains that solids are packed closely together, liquids to an extent, and gases very loosely packed with the most weak intermolecular force of attraction between the particles. This is a visual explanation of what we just discussed. Move on to thermal energy and matter, the condition where thermal energy is being supplied. When thermal or heat energy is provided to objects, the atoms and particles in it begin vibrating rapidly at higher kinetic energy and jostle or push their neighboring atoms, hence, energy being transferred throughout the particles. As objects absorb heat, the forces of attraction between the particles begin to weaken and the bonds may break, resulting in change of state. This is usually termed as an endothermic process where heat is being taken in by the object to change state. Example from solid to liquid to gas. Solid to liquid would be melting, liquid to gas would be evaporation or boiling, and directly from solid to gas is sublimation. Through this experiment, melting of ice, shot via time lapse, we can observe how solid ice converts into liquid water. Thermal energy being produced. When there is a reverse in the change of states, that is from gases to liquids to solids, heat energy is produced by the object itself. This is termed as an exothermic process. Here, during changing state, the object or piece of matter releases energy, such as condensation when gas turns into liquid on touching a cool surface. Freezing is when liquid solidifies into a solid, and deposition is when gas directly converts into a solid. With the help of a diagram given here, we can understand the different changes of states in an easy way, such as solid to liquid is melting, whereas liquid to solid would be freezing. Liquid to gas is boiling or evaporation, gas to liquid is condensation. Solids to gas is sublimation, and gas to solid is deposition. An important point to remember is that whenever there's a change of state taking place, be it boiling, freezing, or any other change, it always takes place at a constant temperature. Until all the particles in the given matter receive heat or supply, the temperature will remain the same, not drop nor rise. Water as an example. Water is a universal solvent and used for various purposes. Its freezing and melting point is around 0 degrees Celsius and boiling and condensation point around 100 degrees Celsius. Now, based on these facts, we can derive a heating and a cooling curve. In this diagram, we have a heating curve. According to the graph, the flat plateaus indicate a change in state. When water is below 0 degrees, it is ice only. However, at 0 degrees, the ice may begin melting or freezing, where there's a state change and depending on the type of curve. This happens only and only at a constant temperature. Up till the point where it reaches 100 degrees, the water is being heated, according to this graph. At sharp 100 degrees, water begins boiling or condensing, insinuating a change in state, and this also depends on the type of curve. Therefore, changes of state takes place at constant or same temperature. This is because all particles undergoing the change have to release or absorb thermal energy present in doing so. Liquid turns into gas by two ways. One is evaporation and the other boiling. Now, both take place at different temperatures. Evaporation is quite a natural and slow process, whereas boiling being an artificial and rapid process. Evaporation takes place only and only on the surface of the liquid, but boiling takes place on the whole bulk of the liquid, that is from top to bottom. Evaporation occurs over a range of temperatures, but boiling only occurs at a constant temperature since the state changes from liquid to gas and the liquid vaporizes. In evaporation, bubbles are not visible. However, in boiling, the bubbling effect is quite visible. Example, boiling point of water being 100 degrees Celsius. Now let's look at a few examples. Number one, melting of an ice cream candy or popsicle, which is quite a common example. Number two would be evaporation of water from a puddle on a rainy day. Number three is sublimation of iodine, where the element iodine sublimes into purple vapor suspended in the surroundings. Then would be freezing of water to ice, mainly at 0 degrees Celsius, as we know the freezing or melting point of water. Then would be condensation when gas touches a cool surface, turns into tiny droplets of that liquid. Lastly, we have deposition where a gas directly turns into a solid. Temperature. Quite a common word and is pretty much used in our daily life. Recently, in the coronavirus or COVID 19, we were all checked of our temperatures to check if we had fever or when you fall unwell using special thermometer guns. Also, it is used to check forecast of the weather and most commonly used in ovens and microwaves in the kitchens to warm or prepare food. But what is temperature exactly? It is a physical quantity that measures how hot or cold an object, body, or surrounding is. It's usually measured in degrees Celsius, Kelvin, and Fahrenheit. These are the following conversions: Celsius to Fahrenheit, Celsius to Kelvin, and Fahrenheit to Kelvin. The reverse could be done by making specific subjects and then formulating the formulas. Moving on to internal energy, which is a part of thermodynamics. It is denoted by a capital U. Internal energy is nothing but the total kinetic energy plus the total potential energy of atoms or particles in a molecule. It is usually associated with vibrational motion and electrical energy of atoms within molecules. Now, potential energy is the energy of an electrically charged particle in an electric field. This is present due to attraction between atoms in molecules. All particles do have kinetic energy, but the amount each particle has depends on the state and then the temperature being supplied to the particles. Like solids do not move, but they do vibrate in their fixed positions, whereas gases freely move. So, comparatively, gases have a higher kinetic energy than solids. Thereby, an object's internal energy is the kinetic energy from random motion of particles and the potential energy from movement of electrons in its atoms. As a system's temperature increases, molecules' kinetic energy will increase or become high compared to the previous kinetic energy they had. Hence, the internal energy also is high. However, If the system's temperature decreases, the molecules will have a decreased or lower kinetic energy, which results in a low internal energy state. Potential energy and kinetic energy are two different types of energies, and the diagrams given here explain the way in which they could be described or seen in reality. Now we have two conditions to look at. First is a hot glass of water, where the molecules and particles would be vibrating rapidly at high speeds and high frequencies with a high or increased kinetic energy, therefore having or possessing high internal energy. In the second condition, it is a cold glass of water, where the particles or molecules will relatively vibrate at slower rates and frequencies, therefore having a decreased or less kinetic energy compared to the previous condition, and hence resulting in a low internal energy state. So that was all for the content. Let's brainstorm and gauge how much we learned from the video. So let's get started. The first question. A substance can exist in three different states: solid, liquid, or gas. Each of the two statements below describes a change of state. Change 1. Particles move much closer together but continue to travel throughout the substance. Change 2. Particles stop traveling throughout the substance and just vibrate about fixed positions. What changes of states do these statements describe? Now we have options A, B, C, and D. Read the question carefully and underline keywords before answering. Which row about boiling and evaporation is correct? Option A. Boiling takes place only at the surface. Evaporation takes place only at the surface. B. Boiling takes place only at the surface. Evaporation takes place throughout the liquid. Option C. Boiling takes place throughout the liquid. Evaporation takes place only at the surface. And option D. Boiling takes place throughout the liquid. Evaporation takes place throughout the liquid. Question 3. When a liquid evaporates, some molecules escape. The temperature of the remaining liquid changes. What is the effect on temperature and from where do the molecules escape? Temperature of liquid and molecules escape from option A, B, C, and D. Lastly, thank you for being an amazing audience. I hope you learned something from the video and, of course, enjoyed.